Hello everyone, I'd like to show you how you can get more out of your C++ code. How you can run your C++ code not only on CPU or CPUs, but also on GPUs, FPGAs, and other devices. How you can run your C++ code not only on Intel or AMD or NVIDIA, but on all of them or many other vendors, and what are the tools that can free up your code to do all of this. But before we even begin, just for a quick introduction, my name is Guy. I'm a technology evangelist for Intel, and you can look here for my YouTube channel. Just look for oneAPI at YouTube, or feel free to connect. This is my LinkedIn profile, and feel free to reach out and ask anything. So the future is open, parallel, and heterogeneous. And if you are already a C++ programmer, it's easy to get there, and I'll show you exactly how. But before we talk about the future, let's start with the past. Let's remember how did we get here. So the lady you see here, I don't know, you might have seen her. Her name is Margaret Hamilton, and she was the leader of the team who coded the Apollo guidance computer. She's standing next to her, the printout of the code. You see that it's not readable, very difficult to code, to debug and understand, but we have landed aircrafts using assembly. But when we move to higher level abstraction, like OpenCL or CUDA, for example, we saved a lot of effort because, one line of CUDA or OpenCL can replace 100, sometimes more, lines of assembly. So why not? And if you move to C or C++, now we can actually read it. There are loops, there are conditions. You can actually see the algorithms that we're trying to implement. And moving even higher to Python, this is almost natural language, right? You can see here for each row, for each column, do this and this. But, it doesn't stop there. I mean, coding is not the target. Products are the targets. So people want to go even to a higher level of abstraction. They want to go to low code and maybe even no code. And this is not a dream. And this is happening today. You can design very nice web pages, a full e-commerce online store, and even sophisticated games without writing even one line of code. Just pick up the character or purchase it on the market, pick up the scene, define the character moves, and so on, and you got a game. Not even one line of code. So why not? And the reason we're going to higher abstraction level is, of course, productivity. If one line of Python code can replace 100 C++ code, then I can do everything faster. Or alternatively, I can do more in the same time. And in addition, it's easier and take less time to get to a good programming level in Python. And it's not only that I can do more at the same time, it's easier for me to get more developers, as there are more Python developers than CUDA or OpenCL experts. These experts, that we sometimes call ninjas, are hard to find and expensive to hire. And many times they have a lot of experience, but on a very specific platform, so they can code CUDA really well, but not anything else, right? So when you're moving up the stack to higher abstraction level, you're moving from developers, from coders, from ninjas, to content expert, to researchers, to entrepreneurs. This is a much larger community. They're connected to the science, they're connected to the business, but they do not know, or maybe do not even want to, code. One of the problems with going up the abstraction level is that sometimes it means going down in performance. And this is what we call the ninja gap. The performance we're losing by not coding directly in C++, for example. And the performance gap is just growing. There is, on one hand, a huge pressure on productivity to get products faster, but there's also a huge demand for more compute power. And for decades, Moore's law was our guiding light, our beacon, our performance scaling goals. The original law or prediction, actually, by Gordon Moore, Intel co-founder, talked about scaling the number of transistors. But I've seen variation of this prediction to predict almost anything. Now, this is all good, but looking at AI workloads and the development of the models, the demand for more compute is growing at a higher rate. And when you talk about the ability to solve more and more of the world's problems using AI, AI is just expanding to more and more domains and is everywhere. Now, when the building blocks are not neurons, but transformers, the demand for compute power is just skyrocketing. And we cannot scale performance using generic monolithic pieces of silicon anymore. The only way to feed this hunger for compute power is by using specialized hardware. And I brought here an example of AI compute demand power, but HPC and other domains have their needs. And the workloads we are running today are just getting more and more diverse. And I can take these workloads and run them all on my CPU and get some performance results. As you can see here, CPUs can usually run everything, any piece of code. But when the workload we're trying to run is very specialized, for example, rendering 3D graphics, our GPU, as powerful as it is, cannot compete with an architecture that was built specifically to execute such a workload, a GPU, for example. You can see here in the diagram that the GPU can run a smaller set of applications, a smaller set of instructions, but with much higher performance. Or we might have an AI accelerator like Intel VPU or Habana Gaudi 2 processor that might look like that. It can only run two workloads, maybe TensorFlow and PyTorch, but with a much higher efficiency. Or other examples like FPGA that you can theoretically program to the range of application you want to support. And this is exactly why we need accelerators. We cannot compete with an ASIC. For specialized workloads, we need an accelerator and specialized hardware. And the truth is that in order to cover the full range of applications, we usually need two. We usually need the CPU, a host, and an accelerator, what we call heterogeneous system. And lucky for us, Intel and other vendors has all the options, all these devices. We don't have only CPU, GPU, VPU, we have XPUs. And I see so many specialized hardware being built up. A few weeks ago, I just heard about YouTube building their own specialized video processing chip and more and more. And it's not only that we have these so many types of specialized hardware, we know how to connect many of them together to build and construct even bigger supercomputers and specialized computers. For example, you can see here two Sapphire Rapids, two next generation CPUs alongside six Ponte Vecchio, the next generation GPUs, in one rack that is being built by Intel. And you put more than 50,000 GPUs and about 20,000 CPUs together to construct Aurora to achieve 2 exascale compute power. This is pretty impressive. But the truth is that silicon is just sand without the software. Without software, it's useless. And if I'm a software developer, I don't care if you have there a GPU, a CPU, thousands of them. What I really want to do is I want to treat the system as a one monolithic entity. I want to take my code and just throw it to this machine. I don't care what's inside. And it's more than that. I don't want to just throw my code to the machine. I want to throw my code to any machine, right? If the national labs in the US have, from one generation to the other, a different CPU from Intel, AMD, or in a different GPU from NVIDIA, AMD, or Intel. I don't want to recode again and again. I want to reuse my code from one generation to the other, which makes a lot of sense. And you don't have to go far to supercomputers to understand that. Think about a day-to-day scenario, like you watching Netflix and you watch it on your widescreen TV, and then you want to take it to the living room on your tablet, and then you want to continue the TV show on the road on your mobile phone, for example, right? In today's world, it sometimes means that the same application, the same viewer in this case, has to be recoded, recompiled, re-optimized for any of these operating system and devices. And this is not what we're looking for. This is not productivity. What we are looking for is for software that could be ported from one device to the other, that will have good heterogeneous capabilities, so I can run the same code on CPU, GPU, or FPGA and other. And of course, I prefer that it is open standard, open source, and cross architecture, cross vendor, and so on. And this is exactly what oneAPI provides me. And I'll show you a few examples in a few minutes. oneAPI is an industry initiative to unify software stacks and to work across devices, architectures, and vendors. There are already many partners involved: universities, research centers, and commercial companies. They're all working together to define the specs, to build the compilers, the libraries, and the tools. And they all provided with oneAPI. There are already tools in the markets and forums that you can take part in to help define the specs and the standards. And of course, Intel has its own implementation of oneAPI, and it's free, open source, open spec, and works cross devices. What it means is that if you're working with oneAPI, no matter what types of applications you're coding, and no matter what devices or systems you're using, the software stack is unified. Most of the libraries, tools, and languages you will find here are not new, okay? You can see here just a few examples. These are being available for years on Intel CPUs, but with oneAPI you can expect the same experience on multiple devices. So VTune, for example, cannot run only on CPU, but you can run it now on GPU and FPGA, for example. And you can get all of these components standalone, each by itself, or packed into toolkits. For example, this is the Intel oneAPI base toolkit. You can find here everything you need to get started in one package. And I wanted to show you one component of each of these categories. We'll go one by one, and I'll try to show you the oneDPL library, how you can use STL, C++ STL libraries to code for heterogeneous system, not only for CPU, but on GPU, FPGA, and other. I'll show you the data parallel C++ compiler, basically SYCL, and the compatibility tool, or the open source version, the Cyclomatic, that can help you migrate CUDA code to C++ with SYCL, and the Intel Advisor, a very powerful set of capabilities to help you get more out of your code. And I'll show you everything working and with examples. So the first one is oneDPL. oneDPL, or oneAPI Data Parallel C++ library, is a library that basically brings heterogeneous or multi-accelerator capabilities to C++ STL library. So the easiest way for me to show it is by example. So you see here a vector of data, and I initialize the vector using random numbers, and I sort it begin to end. And this is simple C++ 17, nothing new about that. And now I can add parallelism by using parallel STL execution policy. So I define here an execution policy, It could be sequential, but it could also be parallel execution. So parallel execution is here, and this is parallel STL. But now I want to take it to a heterogeneous platform. So all I have to do is now read the right libraries and change the execution policy to oneAPI execution default policy in this case. And in this case, the sort will run, which is the heaviest function here, will be offloaded and be run on GPU. No coding required. Change the policy and it's there. Let me show you how it looks like on my laptop. So vector, I'm just taking a large vector and I'm generating random numbers to initialize the vector. I use a sort function to sort it from begin to end, and let's build it. And this is running on my laptop with no problem. Now let's add execution policy, and I can, for example, run sequential policy and apply it to these both functions. And when I run the code, I can see that it's running and one thread was actually executed. Now let's change the policy to parallel execution policy and rerun it. And now you can see that this is running build and running on multiple threads on my laptop again. But this is still, everything is running on my CPU. And now I want to move or offload stuff to the GPU. So all I have to do is to take the execution and algorithm libraries from the oneAPI ones and now change the execution policy to data parallel C++ default policy, which will offload basically whatever the policy applies to my GPU. Here the generate cannot be applied because random numbers are not supported. But let's run the code and now you can see my GPU utilization and you can see that it's been highly utilized. So all this code, the majority, the main computation is now being offloaded to my GPU. And you know, my alternative to do that, I didn't do any code change, just change the policy, took the right libraries. My alternative was to learn OpenCL or CUDA and install all kind of stuff on my laptop, and you know, it's not needed. So I think it's pretty elegant way to take existing code with minimal effort and offload it to an accelerator. I think it's a pretty nice value to developer. All you have to do is install the base toolkit. You can even install just the oneDPL library, and no need for code changes, as I said. And I think this is pretty cool. Getting started with oneDPL is very, very easy. Just Google, just search for oneDPL and go, for example, for the GitHub page of oneDPL, and you can see here examples and everything you need to get started, or navigate to oneapi.io, go to spec, and you can see here the spec of all the libraries and of course of oneDPL as an example, and everything you need, the API, the extension, everything is here for you to get started. All the documentation are there. Next is direct programming using SYCL. So I look at SYCL as a heterogeneous parallel extensions to C++. Data parallel C++ is basically Intel implementation of SYCL. It is the Intel compiler that can now process also directives. This is how I refer to from SYCL. And SYCL brings to C++ exactly what it's missing for parallel heterogeneous computing. The concept of an accelerator devices, the ability for operating disjoint memories, exception handling from devices code, and more. It's based on ISO C++. It is a single source, asynchronous, event-based, and there are already many real examples and big community around it. The SYCL compiler is basically the good old C++ compiler that can compile your C++ code as before, but now can also compile SYCL code in parallel and generate heterogeneous execution program. The device code for the accelerator or GPU, for example, and the host code for the CPU to handle the CPU code and the interaction between the host to the accelerator. And here is SYCL in a nutshell. I believe we need three types of capabilities if we want to be able to program a heterogeneous system. First, we need to be aware of the system. So device discovery and information is a must. We want to be able to know if we have in the system a CPU or also a GPU or other devices. We would like to have information on these devices. It could start by capabilities like number of execution units or vendor, and it might even be real-time information like what's the utilization of this device, or even what is the current temperature of the GPU. The second is the ability to control the device, to dispatch work to this device, and to be able to know the status of the execution in real time. And the third capability is the ability to exchange data efficiently with the device. As you know, in many cases, the compute is sometimes not the issue. I can offload some work to the GPU, for example, but transferring the data to the GPU back and forth is just killing the performance. So this is a simple piece of code you can add to your C++ program. You can see here the notion of platforms, and you can see which platforms are connected to my system and which devices are available. And for example, if I run this code on my laptop, I see that I have a CPU and I also have a GPU and other devices, and it's been discovered. So now I can select the device I'd like to use and assign it to an execution queue. Here, for example, I'm assigning queue to the host, okay, to the host. So by using the host selector, basically my CPU. So now there's a queue to the CPU, and I can also assign a different queue to the GPU. And you can see that I can query multiple properties of the device. So I could even build custom selector and choose only a GPU that supports FP64 and designed by AMD, for example. And the next level is dynamic resource allocation and optimized for throughput or latency or for power or for price, whatever you choose. The second capability is controlling this device. So I have a queue connected to my GPU, as you can see here, and I can submit work using a handler to this GPU, to this queue. So the code here inside these curly brackets will run on my GPU or any other device I will choose. So it's a simple C++ code that using this SYCL directive I could run on my CPU, or if I choose on my GPU or any other device. And now we need to think about the data. Data has to be shared across devices efficiently. So we have two main ways to do it with SYCL. The first is by using buffers. I assign here a buffer called A, and here inside the device code in the kernel, I need an accessor to access that buffer. But this array, this A or accessor A, is visible both to the host, to the CPU, and to the accelerator, the GPU in this case. I find the usage of buffers to be very elegant, but you can also use unified shared memory if you prefer this style of coding. So instead of allocating a buffer, I'm using here the good old malloc, and in this case, malloc shared. So this memory, this range of memory will be shared between the host and the device. And there are, of course, multiple ways to do that. But the nice thing is that the data, our array, is visible to all devices, CPU, GPU, and others. So it's pretty readable and in line with your current C++ code style. So as you can see, I don't think there's a huge investment to move from C++ to C++ with SYCL. The additions are not very big, and the return you're getting is huge, because your code can now run on any CPU, on many types of GPUs. As you can see here, you just need to choose the right compiler, but you can see here GPUs by NVIDIA, AMD, Intel, and others, FPGAs by Intel and Xilinx, and more backends are being built. So once your code is SYCL, it is free to run on multiple platforms, and I think this is a pretty powerful capability. The problem might be if you don't have C++ code, but you have CUDA code, and we have some new tools that could automatically help you convert CUDA code to C++ with SYCL. Intel migration tool can do 90-95% of the work automatically. Cyclomatic is an open source project that's doing basically the same. There are many examples and test cases online. Just look for them. So if you want to run your C++ code on CPU, GPU, FPGA, and other devices, but what you have today is a CUDA source code, then you can automatically migrate your CUDA code using Cyclomatic. The new automatically generated SYCL code will have comments and instructions if manual code changes are required, and I'll show you a few examples. And then all you have to do is to build the code with your preferred compiler to your target device or vendor. It has many details, and I've seen quite a few success stories, people who've done the conversion with really minor effort. And there are differences. CUDA and C++ with SYCL have different ways to report and handle errors. Thread IDs in CUDA looks like local identifier in SYCL. So there are different ways to code and to allocate memory or buffers and so on. But I found it pretty easy to understand, and you can easily improve it if you need, because it's open source. I'll just show you one example of a code I tried to convert from CUDA, as you can see here on the left side, to SYCL, to C++ on the right. And you can see here how, of course, the libraries are different and being brought automatically. The buffer allocation looks different. And the actual kernel is being built here. And there you get in all kind of comments. For example, the error code is different, which makes total sense. And try it. Just Google Cyclomatic and take your CUDA code to C++ and open it up to so many opportunities. So if your code is not CUDA, but rather C++ code, Intel Advisor, just one of the tools applied with oneAPI, is a great tool. It can help you analyze the code, understand the dependencies graphically. It can help you with better threading, better vectorization, and more. For example, you can see here how you can analyze your code, see the dependency flow graph, and a great way to explore dependencies and understand the code flow. There are capabilities to help you identify best candidates for parallelism, prototype threading, and check if there are data dependencies preventing parallelism that the compiler cannot exploit. Modern compilers knows how to vectorize, but sometimes they take the safer side, and sometimes with small rewrite of the code, they can do much more. Intel Advisor can help you improve your application performance with actual recommendation of how to fix vectorization issues. The roofline analysis is pretty cool, and I'd like to show you how it works in 2 minutes. So your code has many functions, loops. Each has a different arithmetic intensity. A function that adds B and C into A is less complex and takes less operations than calculating the cosine of B and multiplying it by B and C or something. This is measured basically by the number of operations per byte of data, the x-axis. Now, each of these functions has a compute intensity, but how fast can they run? And this could be measured by flops per second, which is the y-axis. Now, the arithmetic intensity is theoretically at least fixed, so cannot move right or left, but can run faster or slower depending on the software implementation, or the hardware it uses. So can move up and down the graph. Our hardware has its limitation. For example, the red line here is the maximum flops per second this CPU can execute. But sometimes the problem is not the compute, right? Sometimes our memory bandwidth can also limit us, as you can see in the red line. And when you combine these two lines, they form what we call the roof line, which represents the maximum performance our machine can supply. Theoretically, each of these functions could be improved all the way up, but this function, for example, is hardly used, and improving it won't help the overall program performance much. So the advisor just color it green, and this function is already optimized. So optimizing it further is a big effort and doesn't worth it, so it's colored yellow. And this function is colored red, as the advisor advised us to invest our time here. I think it's pretty cool. The truth is that representation of the hardware is a little bit more complex. As you can see here, different roof lines for vector operations and for scalar ones. And the memory story is also a little bit more complex with hierarchies that imposes different limitations. For example, the level 1 cache is faster than the level 2, but the level 2 has a bigger capacity. This is how a real analysis look like, where you see the roofs representing the maximum capacity of the machine. Each of the circles here is a function of inside the code, and the advisor located in on the graph and color it with potential performance improvements. So check out the roofline analysis. I think it's pretty cool. And the last capability I wanted to show is the offload advisor. Imagine you have a heavy C++ application with many lines of code, loops, and so on, and you would like to improve the performance by offloading the right portions of the code to an accelerator. But which portions of the code to offload, and by how much will the code be improved? And offloading code to an accelerator costs, the memory traffic back and forth. Can we take this into account? The answer is yes. This is exactly what Offload Advisor can do for you. And this is what you see here is the main dashboard. And you can see here, for example, my code has 3 regions or 3 loops that could be offloaded to an accelerator. And you can see the 3 of them right here. These 3 loops include 75% of the overall code. So I can improve these 3 loops, this code, by 50%, by 50%, which will improve the overall application performance by 10%. And you have here all kind of information. For example, the memory bandwidth, what's limiting the performance, and so on. So to give you a quick example, I'll open the Intel Advisor, and I'll choose the offline modeling, and I can choose many different Intel GPUs as my target platform. I'll just choose Gen 9 GT2. My baseline is i7 CPU, and I have the results, and I can speed up only 1% of the code. This 1% can be speeded up by 50%, but it's, the result of the overall code will be 0.7%, not that much. And I can see the actual loops that, I'm advised to offload. This one is bounded by level 3 bandwidths, and I can go to the accelerated regions and actually look inside the code that I was recommended to offload to a GPU. Let's get inside the code itself, and it's loading, and you can see here that this is really an actual kernel, which makes sense and can be improved by 40x, this specific loop, if I just take it from the CPU to the GPU. I think it's pretty cool. It just pinpoint you to the right places in the code after, thorough analysis, and even give you the hints on the estimated performance. And I think this is a very powerful tool and pretty cool. You can search for Intel Advisor on the web, and there are multiple ways to actually get it. You can download the full base toolkit or download it standalone, or you can even try it, without installation at all, remotely on the Intel Dev Cloud. Just look for Intel Dev Cloud. It takes 2 clicks to register, and you have access to multiple machines. They're all installed, they're all ready to operate. So this is all for Intel Advisor. And to summarize what I've said, I think, like I said, the future is open, it's parallel, and heterogeneous. It will have multiple accelerators, and the fastest way to open your code to multiple devices by multiple vendors is probably to add SYCL to your C++ code. And I've showed you how to use library functions, and I've showed you how to do direct programming, and how to take CUDA code and convert it to C++, and how to use Intel oneAPI tools to analyze the code, to get advices on vectorization, on offloading, and so on. I think it's a pretty powerful tool. More information you can find at sycl.tech or at oneapi.io. And of course, feel free to navigate to my YouTube channel. Lots of information over there, and you can leave me a feedback. I'll be happy to hear your questions. Thank you very much for your time, and good luck.